I'm assuming, right?
Yes, yes.
Okay. Thank you. Thank you for that wonderful introduction. Um, I did spend 2 exciting years at CERN many years ago, from 1982 to 84, when the W and Z particles were being discovered, and had the good fortune to work with Simon van der Meer and Carlo and all those people. So it was a wonderful occasion. So I have been an accelerator physicist all my life, but lately I am turning my attention to maybe we should be a bit smarter and try to do small scale experiments in a laboratory while we wait for large colliders to be designed and funded, and that's taking now 10, 20, 30, 40 years. So um, I hope there are 184 participants. I hope there are quite a few young ones in there, so I can motivate some of them.
I have no idea.
Right, okay. So I have given you a little outline of my talk. I'll briefly talk about the importance of instrumentation and sensing, both classical and quantum. Then I'll quickly give you an idea about the marvelous discoveries of particle accelerator-driven particle physics. That I will follow by um, challenges of unsolved problems of particle physics, in particular events from the very early universe and the dark universe, dark matter and dark energy. I give you only a few examples of these clever experiments. I cannot talk about everything. It's a huge field and it's growing very, very fast. And then I'll touch upon how these quantum sensors are also extremely important for other branches of science like neuroscience and life science and so on. Before I proceed, I want to thank Wolfgang and John Francesco Giudici for inviting me to give this talk. I have been heavily involved with US DOE and NSF quantum initiatives and programs, learned a lot. Currently, I'm involved with the US SNOMAS 2021 study groups, and I have also been involved with the European particle physics strategy. And so I'll be borrowing a lot from those contributions. And in particular, I've learned a lot from my colleagues, Aaron Chu at Fermilab and Jason Hogan at Stanford University. So I want to mention these before I proceed, because most of the times we forget giving credit to people that we learn from. So historically, instrumentation is the key to discoveries. As you know, it's a great enabler of measuring anything scientific. Galileo said many centuries ago that measure what is measurable and make measurable what is not so. And great British scientist Sir Humphrey Davy said nothing tends to advance knowledge as much as the application of a new instrument. So we had Galileo's telescope, Newton's microscope, uh, and so on. So these are instruments of science. Um, we have today, in our field at least, great, big, large, grand instruments of science like particle accelerators, synchrotron radiation sources, very large free electron lasers, and intense atomic lasers, and so on, telescopes, satellites, large underground multi-ton deep detectors, and so on. These are very large scientific instruments. And then, of course, there are very small scale atomic and solid state experiments. And this latter scale of laboratory scale and mesoscale, sometimes tabletop, sometimes laboratory scale, or sometimes small lab scale experiments are also now going to be very important for particle physics and cosmology. So I'll try to motivate that aspect in my talk. So most of you know at CERN, those who are logged in, that we have come a long way in the last 100 years, from 1 meter cyclotron to a now 27-kilometer Large Hadron Collider. And now today we are talking about future circular colliders, 100 kilometers. A large number of particle theorists, particle experimentalists, engineers, technicians have contributed to actually what we call the standard model. I grew up in the mountains in India where Buddhism was practiced, so I call it the standard model mandala. You have the 6 quarks up there. You have the 3 leptons, the 3 neutrinos, the 4 gauge bosons, and then squarely planted in the center is the Higgs boson, which was the latest discovery at CERN. Actually, I was lucky. I was actually there in UK, and I could participate in the celebration of this Higgs boson discovery. We discovered and saw a hint of it, but actually we barely understand it. So people are today, considering for the Higgs aspect of it to very large circular colliders like future circular colliders or its equivalent elsewhere, or large linear colliders of electrons and positrons and so on. And the other aspect of the standard model that is still elusive is the funny particles called neutrinos, which actually change their character as they move along the flavor mixing propagation of neutrinos. And for this, there are long baseline neutrino experiments being planned in Japan, Y2K, and in the US by having a very high power, high current proton beams producing high power neutrino beams, and you just let them go to very far detectors and you catch them at various stages as they propagate, as they play this kabuki game of changing their phase from electron neutrino to muon neutrino to tau neutrino and so on. So these are now the existing challenges of standard model, and there are also, of course, many, many things beyond it. My whole pitch to the younger generation is that these wonderful future machines like circular colliders and linear colliders, there is still probably scope for them if we can make an international effort to build very large 100-kilometer scale proton-proton collider or many kilometer scale linear colliders. But while we are doing it, maybe there are complementary ways of searching for the same physics, but on a much smaller scale. So rather than creating the energy density and the energy scale in the laboratory by colliding particles, which is very, very difficult and very, very expensive, I would say that everything from the Big Bang, which happened 13.8 billion years ago, is still there as a fossil or a relic. The signals are very weak, of course, after so many billions of years. But if you are smart, instead of focusing energy on an accelerator to create that field, maybe we can focus on creating very, very weak signals from the early and dark universe by having very clever detectors. And this is what I call cosmic archaeology, meaning you just look for hints of things that are there by very sensitive detectors. I mean, I just do not want to go into the details because it's a very detailed subject. You remember 13 billion years ago, we were talking about the Planck scale. Everything was entangled into just this tiny little object, and the wave function you can imagine to be just a single wave function, psi Planck. No matter what we see today as different galaxies, planets, atoms, molecules, they're all ultimately entangled and correlated originally from the Planck scale, and the signatures of that entanglement must be still there. And we have to be clever to actually discover it. Actually, I know there are efforts going on now to discover quantum entanglement from the origins of the cosmic microwave background radiation. If you look at the polarization of CMB at different parts of the universe, you may be able to see signature of entanglement from Planck scale left over in the CMB. I am an experimentalist primarily, but also a theoretician, but some of you who are experimentalists, just to give you an idea of what we are talking about. If you look at the expansion of the universe being more accelerating than what we expected, and look at the dark energy component, that component is about 6.3 times 10 to the minus 10 joules per meter cubed of dark energy that is being created as the universe expands. Now, we do not know the nature of that energy, of course, but if we pretend it is electromagnetic or electric, it is equivalent to 12 volts per meter, which is not a very high field. You can generate by putting a battery of 12 volts across a 1 meter distance, you get that field. But of course, if it's a constant field, it's a bias. You can never detect anything. You have to have a fluctuating field in space-time to be able to detect it. But dark matter field is even higher, like 10 kilovolts per meter. If you compare these to what has been measured already in the lab for Casimir effect, for example, in 1996, 4 times 10 to the minus 10 newtons per meter square, kind of a force or pressure. Cathode ionization, cold cathode ionization gauges can measure similar type of forces. So these numbers are small, but they're not that small. But you have to look for AC time varying effects to look for them. And here comes the new initiatives, which are called quantum initiatives, where you invoke quantum entanglement. Now, every instrument today is, of course, based on some kind of a quantum phenomenon at the very bottom of it. Whether it's a voltage or a current or a charge, you're getting it from a silicon solid state device or a photoelectrons coming in a, but we have not really exploited the true quantum nature. We have to look for signals which are actually coming from a deep quantum entanglement and then manifesting it in a signal. We have not been able to exploit quantum entanglement in quantum instruments. Sure, you have silicon chip detectors, you have photoelectron detectors and stuff, but they are quantum devices, but not based necessarily on quantum entanglement. So just to give you, for those students, if you think about quantum mechanics, there's a very fundamental limit of whenever you measure anything by quantum pulse, you cannot avoid but giving a little noise or a kinetic momentum to that particle by simply the fact that you are exchanging a quantum h bar omega with the particle of mass ms. And if you put a nanogram at 1 kilohertz, you get 1.5 million electron volt kick. Or if you get an electron mass at 1 kilohertz, you get a 1 micro electron volt kick. These are quantum recoil or quantum back action given by quantum mechanics, Heisenberg. You cannot really avoid it. But now, today's quantum science and engineering has found ways to beat quantum mechanical limits of quantum zero-point noise by techniques of squeezing, non-demolition measurements, where you actually measure something without destroying or creating a photon. You can transport quantum mechanical states. The whole field of quantum microwave electronics has sprung up. And so I'll give you some examples of these in the future, okay? And before I give you examples, these, if you can implement these quantum sensing, where you are using sensors that are actually dependent on quantum entanglement at the very bottom of the measurement process, you can actually open the door to many, many interesting areas like detecting very light dark matter candidates like axions or hidden sector photons. You can scatter or absorb dark matter particles. You can measure very, very small electric dipole moments of electrons, protons, neutrons. You can measure very weak gravitational waves left over from the Big Bang, like a cosmic gravitational wave background, like cosmic microwave background. There is a big tremor of the creation of space-time at the Big Bang. And you should be able to measure that tremor that's still there as an aftershock today. Dark energy, variation of fundamental symmetries, and maybe new forces and particles and so on. So let me quickly, very simplistically explain to you why quantum entanglement allows us to reach deeper than classical measurement. If you consider two independent observables, X and Y, you can measure X to the best you can and measure Y to the best you can, but they are still independently in phase space. They occupy a certain volume and you cannot change much what you do. But somehow, if you can find and create an entanglement or talk about a quantum mechanically entangled system that connects X and Y, then you can actually And if you're not interested in the observable Y, but only in the observable X, you can scatter all unnecessary information into Y for the sake of increasing your resolution in X. So this technology called squeezing, which takes advantage of quantum superposition, Heisenberg's uncertainty principle, and quantum entanglement, allows you to squeeze information into one dimension at the cost of others. So if you have a radio frequency microwave circuit that is dominated by white noise, thermal noise, quantum noise, you can actually eliminate a lot of this noise by quantum squeezing. So when you see a real signal of a photon, you know it is not a noise photon, but a genuine photon coming from somewhere. So just to give you an example, if you look at a radio wave or a microwave, sine or cosine gives you the two quadrature components, or you can think of it as amplitude and phase, or position and momentum for a particle. But in order to measure the wave amplitude and phase simultaneously, you encounter a quantum limit, which is a quantum of phase space area, which is half h bar. So there is thermal noise given by the temperature of the system, half kT, and then there's a single photon per resolved microwave mode of the system that you're trying to measure. And today's technology of yesterday's cannot distinguish between a noise photon and a signal photon. And so exotic searches for very, very weak processes become noise dominated. Now, if you don't care about the phase, but only you want to count the photons that are there, you can actually scatter all the information in 2 pi in phase. But you want to count the amplitude as precisely as you can. And now there are techniques called quantum non-demolition techniques, invented by Harosh and Wineland, got Nobel Prize in 2012, where you can create a process where all the back reaction from the photon scattering is put on the phase. You scatter all the phase out, but you count actually the photon number operator commutes to the Hamiltonian, so you do not destroy or create any new photons. So if there is a undesirable new source of energy coming from a process called new photon appears, you know that this is a signal photon and not a noise photon. To give you an example, if you look at typical microwave circuit noise spectrum as a function of frequency, I have plotted here on the dashed curve the typical standard quantum limit, and the red curve on the top is actually the what you can achieve by this non-demolition technique at a rather high temperature. It's low temperature for most people, 2 degree Kelvin, but still pretty high, and it lies above the quantum noise limit. If you go down to 100 millikelvin, the purple line, you are beginning to go below the quantum limit. Now, if you go to 30 millikelvin, you actually go almost entirely below the standard quantum limit. So linear amplifiers suffer from the standard quantum limit, but using this technique, you can actually use QND techniques to measure noise, which now becomes completely black body dominant and not quantum dominant. It depends on temperature, and if you go down to 0 temperature, your noise should go down with temperature and not be limited by finite floor of quantum noise. So in RF language, radio frequency or microwave language, if you imagine a lumped circuit which is being activated by a exotic voltage coming from a particle that you do not see typically, but maybe it's a dark matter or an axion or some kind of a strange particle, is giving you a very low and weak signal, which you have converted into a microwave photon. Typically, the resonance line is a total resonance of the LCR circuit, but it has a white noise floor, and it has a thermal background, has a photon back reaction background, and a vacuum fluctuation background. What this technique does is reduces all these quantum noise limits so that you can actually raise the sensitivity to the photon by fact 4 or 6 orders of magnitude beyond. There are all kinds of detailed quantum mechanical up and down converters using Berry's phase, Josephson junctions, and so on. I'm not going to get into the detail, but it's a very detailed and evolving, emerging quantum electronics using quantum non-demolition techniques. So the whole idea is you have to create a macroscopically entangled state, which is a quantum state. It is macroscopically entangled, but you have to keep that quantum coherence for a finite length of time for you to be able to measure anything. If it just lasts for a 10 to the minus 31 seconds, you have a hard time detecting it. But if you could keep the quantum coherence at a reasonably macroscopic time, like a microsecond or a millisecond or a nanosecond even, you have a chance of creating a quantum entangled macroscopic system like a micrometer scale at a millisecond time frame. So today we have very fancy quantum sensors like you know about the superconducting quantum interference device called SQUID, which can detect 10 to the minus 16 Tesla per square root of Hertz, kind of a magnetic field spectrum, which is very, very sensitive to signals coming from exotic particles or even brain waves or uh, uh, neuroscience and so on. You have atomic sensors through atomic gravitometers, accelerometers, which can detect 10 to the minus 13 times the Earth's gravitational field, G, per square root of Hertz. And you can apply these atomic entanglement techniques to detect very small fluctuations of space-time that exist even today, left over from the Big Bang. I'll give you an example of that today. So I'll give you two examples of detecting axion or light dark matter or dark photon by microwave cavities using quantum sensor in the middle of an RF cavity. And I'll give you an example of an atomic beam, atomic interferometer to detect gravitational wave from the Big Bang and dark matter. So I have been talking about this for quite some time. So we have been drafted to have a DOE roundtable on it some time ago, 2016, which came up with a white paper some time ago in 2016. The year after, there was a big meeting of big companies like Google, Microsoft, IBM, big universities, and national labs. And it created a big quantum program in the United States. You also have such programs in Europe and in UK. It's a program that started in 2018 with NSF and DOE and industry. It's about, eventually will go up to $600 million per year. Today, starting this year, they're starting about 6 to 12 research groups across USA, anywhere between 10 to 25 million per year for 5 years. And there are about, I would say about 6 to 12 groups already funded. So let me tell you a few examples. Quantum sensors are good for dark matter, dark energy detection, detection of early universe. Quantum computers, of course, is the buzz game today, cryptography, artificial intelligence, and so on. Biological signals, neuroscience, new types of correlated materials, like you can create designed materials in the lab, like silicon, but these materials are such that the conduction band and the valence band are very close to each other with the energy gap of 10 to the minus 25 eV. So if you have these particles in the insulator state, so and a particle goes by, a dark matter particle, and deposits a small amount of energy, like 10 to the minus 25 eV, it becomes instantaneously a conductor. And you can detect such small signals by these types of design and materials. So material science can collaborate with particle physicists to create quantum correlated materials and very, very weak electromagnetic signals from geology and so on. Let me start by talking about dark matter and give you an example of how we can talk about detection of dark matter. So as you know, the dark matter, CERN had been chasing dark matter in the form of WIMPs, weakly interactive massive particles. These are very heavy GeV class particles, which are particle-like deposit energy in the detector. So far, our energies have not been high enough to get any detection of any real WIMPs. But more and more people are thinking about ultralight dark matter as a possibility, like axions or dilatons or hidden sector photons. And these are low mass, very high number density, and these would rather act like a classical field or a wave rather than a particle that imparts an impulse. And people have been considering many ways of detecting these wave-like dark matter particles: microwave cavities, lumped circuits, magnetic resonance, nuclear magnetic resonance, spin of the nucleus in special materials, or by atomic interferometers, depending on what mass scale you want to reach, from milli electron volts to about atto electron volt scale. I give you one example of a milli electron volt to micro electron volt detection of axion or axion-like dark matter. If you imagine, we are talking about looking for a signal that is like 1 part in 10 to the minus 25. If you imagine a little lumped circuit in the middle of a cavity, and this cavity is totally isolated electromagnetically, it's a superconducting cavity, so the electric field and magnetic field inside oscillates and stays for a long time as a quality factor of 10 to the 11 or so. And inside you put a quantum detector, like maybe a Josephson junction that acts as a 2-level quantum system or an oscillator of some sort. If you have normal matter, standard model particle coming in, it cannot penetrate, it is blocked. If you have a dark matter, which couples very weakly to ordinary matter, it can penetrate and it can give you a signal. Now you want to make sure that the signal is a signal that you are not expecting from the background noise or the thermal noise or the quantum 0-point noise. It's a real photon coming out from a dark matter, entering the cavity, penetrating the electromagnetic barrier, and spontaneously deciding to express itself as an ordinary microwave photon. So here you use quantum non-demolition technique of looking at the signal of the superconducting device in the middle and span the entire frequency band that is available to this cavity qubit system. What you are doing here is making a coherent interaction of the macroscopic microwave inside the cavity with the quantum mechanical state of the qubit inside the cavity and detect any undesired photon that you did not expect. So this technique is now being used in a superconducting cavity, superconducting qubit system. It is funded by Department of Energy Quantum Initiative Program and by private industry like Heising Siemens Private Funding Agency. If you put this cavity by itself without a magnetic field, you can detect dark axion, dark photons, hidden sector photons. But if you embed it in a very strong magnetic field, you can actually get axions because they can couple quantum mechanically to the electromagnetic field and the magnetic field. So anywhere between 500 megahertz to 100 gigahertz would be the frequency. So you're talking about very weak mass, very small, light dark matter particles, and you can detect it. And if you look at the scientific reach of this kind of a detection, on this plot, I plotted the coupling constant of an axion to the axion mass. And if you talk about a 10 Tesla magnetic field, inside that magnetic field, you embed a 10 gigahertz microwave cavity, or a 1 gigahertz microwave cavity, or a 100 gigahertz microwave cavity. You can span an axion mass anywhere between a milli electron volt to a micro electron volt range that has not been explored in the literature. So you can either detect, find it if you're lucky, or you can exclude it if it does not exist. And it requires technology of superconducting magnet, superconducting cavity, qubits, but it can be housed in a lab like CERN or Fermilab or at a large university, for example. So let me now turn to my second example, which is using atomic interferometry to discover gravitational waves, or you can also look for dark matter coupling to atomic levels. You remember when I was a graduate student, we studied about gravitational waves from Einstein's general theory of relativity, but we never thought that we would ever see it in our lifetime. But a few years ago, two large black holes, actually not so large, they are medium-sized black holes, collided, and there was observation of the coherent gravitational waves for the first time in the 20 hertz range detected by LIGO. Now, you would expect that if you look in this figure in the middle, our current standard model of cosmology, Big Bang, 13.8 million years ago, then inflation, and then we are here today, and during inflation, at the beginning, space-time went through a big tremor. It might even have emerged from the event. And whatever it was, you should expect some level of tremor of space-time left over at the level of 10 to the minus 25, delta L over L relative strain, appearing at 1 millihertz to 1 hertz. And if you had a proper detector, you can detect it. Unfortunately, this frequency is too low for LIGO, because LIGO uses inertially suspended mirrors, which have an inertial noise, seismic noise, that cannot go below 10, 15 hertz. And it is well above LISA, which is space-based, which only starts below 1 millihertz. So the gap between millihertz and hertz is the place where we are looking for gravitational wave signals, and this can be detected by atomic beams. The second thing you can expect, if you look at the Lagrangian of dark matter, various couplings and stuff, dark matter does, if it couples to the electromagnetic sector, either the electron mass would oscillate or the alpha, the fine structure constant, would oscillate. So you would expect the atomic transitions to be fluctuating in space-time by coupling to the dark matter. And if you have a very clever and precise atomic interferometer and spectroscopy, you could measure these kind of fluctuations of atomic levels by coupling to the atomic beam. So we are looking at this band in the gravitational wave between a millihertz and a hertz. I just show you it falls in the gap between LISA and LIGO. And I just want to compare the two for those of you who are not familiar with atomic beams. LIGO uses suspended mirrors, uses laser interferometry of two masses experiencing a gravitational wave going through it, and you have a strain of the distance between the masses, h, which oscillates at the frequency of the gravitational wave. And second interferometer arm is the reference arm that gives you the clock, so to speak. For an atom, you use freely falling atoms, which are not suspended inertially. So it does not have any inertial seismic noise. You use laser talking to the atomic beam, going back and forth, and the flight time of the laser as the time of flight for the interferometer. And the atoms themselves, today we have very good strontium atoms, which are excellent clocks of 10 to the minus 18 to 10 to the minus 19, delta F over F atomic clocks. So atomic phase, laser flight time, atomic interferometry will give you a sensitivity that can approach those that I mentioned. Just pictorially, light interferometer gives you interference fringes of light, intensity of light. Atom interferometer gives you intensity of matter wave, intensity or density of matter after you interfere the two atomic beams. Here I give you an example, atomic beam. You can split it into two quantum states with having two different intrinsic momenta, having two different phases, by putting a laser pulse called a pi/2 pulse that splits a beam into two quantum states. You can then put a pi pulse called a laser pi pulse, which simply changes the momentum state of the two beams. P goes to P plus K and P plus K goes back to P. It's called a reflector. And then you can put another beam splitter, but this time it's a beam combiner, which adds a phase to each one of the beams to bring them back together. And finally, you actually get a quantum interference of the two beams. Here you see the two beams, one with momentum P, one with momentum P plus a K, and they're macroscopically separated in space-time by 10 centimeters or 50 centimeters or 1 meter. So atom is at both places simultaneously entangled. You could not say where it is, whether it is in state P here or whether it's in state P plus a K at 10 centimeters or half a meter away. So it's a macroscopic quantum entanglement of the two atomic states achieved by atomic interferometry. At Stanford, they have done this experiment with 10-meter atomic beam interferometry, and they have macroscopically separated a single atom, quantum entangled separated by half a meter apart. We can talk about now falling atoms at 10 meter, 100 meter, 1,000 meters, okay? And as the atom falls, the phase of the wave function goes as k times z. K is the momentum. You can change the momentum by kicking it with a laser pulses, or you can change z. In a systematic fall under gravity, z is changing as a square of the time of fall. But if there's a gravitational fluctuation, because there's a gravitational space-time metric of a gravitational wave going through our background gravitational space-time noise, then z would change, atomic paths quantum mechanically would change, and you can see that change in the atomic interferometer at the bottom. So you create an atomic cloud, you split it into two beams by laser beam, let them go under gravity, you bring them together by reflection, combine them again, and then eventually at the bottom, you see the atomic interferometry. In the laboratory, if you can see this was done actually at Liverpool by my colleague. You see atomic cloud, 10 to the 6 atoms at 5 microkelvin. You create it, stays for a few seconds, and then it disappears. Then you inject again, and it disappears. And now we are talking about creating this in ultra-high vacuum, which CERN and other national labs are very good about, dropping them 10 meters, 100 meters, a kilometer, and doing atomic interferometry by sending a laser beam up the atomic beam. So if you imagine two such interferometers separated by 1,000 meters or a kilometer, you could actually get a 1 Hertz gravitational wave detector at 10 to the minus 24 to 10 to the minus 23, 25 level. At Fermilab, we have this huge program of sending a neutrino beam from the Fermilab to a very distant detector in Sanford in South Dakota, where we have a kilometer deep shaft. This long baseline neutrino experiment of 1,800 kilometers to study the flavor changing mixing of neutrinos. But eventually we want to do an experiment with atomic beam at a kilometer level in this mine. However, you cannot jump from 10 meters to 1,000 meters. People will laugh you out of the room. So we have to demonstrate an intermediate scale demonstration experiment that atomic interferometer is a proper tool to study gravitational wave and dark matter. Fortunately, at Fermilab, we have a 100-meter shaft. You can see in this place, 100-meter shaft called the Minos shaft, where we can launch a 100-meter atomic interferometer experiment. So this is the 10-meter scale experiment at Stanford. This is the 100-meter shaft at Fermilab. We are refurbishing this shaft And already this shaft exists, and we are now putting in a vacuum pipe of 100 meters deep into this vacuum technology, the core competency of Fermilab. So this is actually perfect for us to do. We have created a collaboration between Fermilab, Stanford, SLAC, University of Oxford, Cambridge, Johns Hopkins, Northwestern, Northern Illinois University to create this experiment called MAGIS 100, matter wave atomic radiometer interferometric sensor. And of course, you can imagine all kinds of systematics, seismic noise, gravity gradient noise, optical noise, but these are systematics, and you should be able to monitor them over a length of time, and by clever artificial intelligence programs, subtract out most of it from the actual noise signal that you will see from a dark matter or a gravitational wave. So these are the measurements of the noise in the shaft that you are measuring, just giving you some example. So this is good, but it is useful to set up two interferometers to see correlations. You remember I told you that everything from the Big Bang is quantum mechanically correlated and entangled. So if you imagine one interferometer and a second one somewhere, and initially you would see no correlation at all. But remember, we are all going through the galactic frame. We are passing through a galactic inertial frame. And as you observe these correlations over a length of time, you will eventually generate correlations between atomic interferometer data, between one interferometer and the next. So you'll get a finite non-zero phase, which has information about space-time correlations of dark matter and gravitational wave created primordially at the Big Bang. So with this in mind, we actually have a collaboration now. You see on the bottom left-hand bottom corner, MAGIS in Fermilab, collaborating with a network in UK called Atomic Interferometry Optical Network, AION, the network. So we want to exchange data and try to correlate our experiments. There are few other European experiments, MIGA in France and ELGAR, and you have Zyga in China. So atomic interferometers are being taken very, very seriously now around the world. Just to give you an experimental reach, so what can you expect to get in terms of, let's say, the ultralight scalar dark matter? Theoreticians amongst us have calculated and estimated that with MAGIS 100 meter, or if you go to a kilometer, which is called the future surf, you could actually reach a mass scale, as we have given here, 10 to the minus 12 to 10 to the minus 16 electron volt in dark matter search. And in gravitational field, you can see between LISA and LIGO, you can get a between 100 meter, a kilometer, and then you can also get a space-based satellite experiment with atomic beam. You can actually figure out quite a few orders of magnitude higher than what is expected. Now, even if you cannot detect any signal from the gravitational wave background from the Big Bang, there could be astronomical sources of gravitational wave in this band which you cannot detect with LIGO and LISA. So it is a new sensor with enough sensitivity to detect both coherent gravitational waves from astrophysical objects merging or incoherent noise-like background from the Big Bang. I don't have time because I want to close up quickly so that there are some questions. There are many other applications of quantum sensors. I talked about new types of materials, Dirac and Weyl materials, trapped ions, cold molecules, nitrogen vacancy in diamond, nuclear magnetic resonance in MIST. So I don't have time for it, but they are really developing very quickly. NMR, for example, you can detect the magnetic field precession of a nucleus by axion wind and can change magnetic moment fluctuation or electric field fluctuation. So people have many, many experiments in the USA and elsewhere, Casper, Quax, Adrian, and so on. Obviously, the enabling technologies are superconducting qubits or Josephson junctions, ensembles of them, low threshold quantum calorimeters, high Q cavities, high field magnets, cryogenics, electronics, computing, and so on. We are already applying the fact that our lab has a very good superconducting cavity core competency. So we're trying to build a 50 qubit, 50 Josephson junctions inside a microwave cavity superconducting to build a 50 qubit prototype quantum computer. It's already funded through a DOE initiative at $15 million per year at Fermilab in collaboration with 5 other institutions. So just to tell you that this is being taken seriously. And as they take the technology, we'll of course skim off in our applications to particle physics and cosmology. Another thing is I talked to you about you are creating an entangled system, whether it's a qubit microwave or an atomic system. Sometimes people call it an EPR state, Einstein, Rosen, and Podolsky state. You can concatenate these states to get a string, and then you can get a cluster and eventually a network. So quantum sensing can be stretched eventually to quantum networks. And so at Fermilab, we are applying this to quantum teleportation experiment and creating a network to send signals encrypted. It's a big program. It's a collaboration with Caltech and AT&T. There's optimization and machine learning applications with various AI applications. There is even a program to mine LHC data much more effectively by quantum annealing algorithm techniques and stuff. I don't have time, but people are applying quantum sensors for magnetoencephalography. Just to tell you that structurally, so there's a lot of aspects of neuroscience, how to understand the brain and intelligence or structure of neurons. It has all the left side of the brain, which is analytic. The right side is supposed to be intuitive. At accelerator-based X-ray sources, people have done functional mapping of the brain, neurons and synapses and stuff. We know a lot about functional mapping, but the biological activity around the brain acts at very, very low magnetic fields of 10 to the minus 14 or 15 Tesla level, and they can be detected by superconducting sensors around the brain. So also people are beginning to look at biological effects on yeast cells and stuff from microwave energy at 40 to 100 gigahertz, millimeter wave, which is not explainable by microwaves, maybe interaction with unknown radiation. I have my colleague Fritz Kaspers at CERN, who is doing a lot of work on this. One can consult him on that. I'll simply close by saying that I've given you only an example of the tremendous potential of quantum sensors for doing what I call cosmic archaeology. Detector development people and particle physics community, theorists, experimentalists actually can benefit from further involvement into this as we wait to mine data from LHC and wait for the next big collider, which may or may not be funded eventually. We also need to train our next generation young workforce at CERN and Fermilab and universities. You know, this is a mixture of many, many disciplines: microwave, accelerator, detector, atoms, molecules, and so on. So I call it the quantum workforce for the 21st century enlightenment. So I will close here, and I want to thank everybody for your attention. So I think I finished in time, Wolfgang, right?
Yeah, perfect. Well, too early actually. It would have taken 10 more minutes plus questions. Anyway, let me thank you a lot for the wonderful talk in you for the whole audience. And I'm sure there are many questions. So please, people, either raise hand or type in the chat either a question or just mentioning they want to ask a question. No questions? Well, I have a obvious question. Maybe it's also an obvious answer. Namely, the nemesis of quantum entanglement is, of course, decoherence, and
Yes, yes.
all your correlations tend to disappear the moment you have the slightest interaction or temperature.
Yes.
And so on.
Yes.
So if you want to measure these extremely small energies, say the remnants from the Big Bang, which are spread out over the whole universe in a way.
Yeah.
So can you expect by sampling a very small piece of this information to get really a meaningful phase correlation out at the end?
Well, we are actually looking into the gravitational wave aspect of it, which you just asked, but let me tell you how we think we can do it for the dark matter and microwave. If you look at, let's say, a ghost particle or an exotic particle, if you imagine an ordinary matter decides to go into the dark sector with a certain probability, and then it propagates, and then it appears as a real particle again somewhere, the entire probability is like 10 to the minus 24 or 25, 1 part in 10 to the minus 25. Today we have superconducting cavities which are Q of 10 to the 11. So you get 10 to the minus 11 from the transmitter side. Another cavity which will detect it, another 10 to the 11, so 10 to the minus 22 from the transmitter and detector, 10 to the 11, 10 to the 11, 10 to the minus 22. And a factor of 10 to the 3 can be easily achieved by cryogenic electronics. So you can reach the sensitivity levels of 10 to the minus 25 by superconducting cavity coupled to a Josephson junction. And we have tested the coherence time of a qubit, like a Josephson junction created in a laboratory, it is a 2-level qubit system inside one of these superconducting cavities. And the two stay coherent together for about, I would say about 10 to 100 microseconds. So that's almost a millisecond, which is almost macroscopic time. So I think the cavity qubit coherence time and resolution is good enough for us to think of detecting dark matter in a coherent signal in a coherent way. The gravitational thing is a bit more tricky. So I think if you think about black gravitational wave like a coherent wave, like two black bodies, like black holes colliding, they generate a ripple in space-time, which is very high and very coherent. So the phase of that gravitational wave is very coherent, and it approaches us, and we can detect it by LIGO or whatever, which is a different thing from the background thermal fluctuation like stochastic gravitational wave coming from inflation era background gravitational wave. And theory is so sparse, people like you should be working on coherence properties of these background inflationary gravitational waves. I don't have a specific answer for you, but we can only say that the signal strength predicted by some estimations, we can probably reach. And we don't expect coherence to last for the length of time of the atomic coherence, but we'll have to see.
Thank you. Now there are more questions in the chat and also raised hands. Let me start with the chat. Can you read actually the chat, Swapan? Do you see it, or shall I read it for you?
Let me see if I can put on the chat. Let's see. You can tell me what question. I cannot quite see it. I have to close before I.
Well, I can read it. Can read them for you too. So
I have a piece of music by Professor Bose. I can play for 30 seconds for your entertainment before we go out. But so just remind me, okay? But tell me, what questions are people asking?
Okay, Mr. Alain Magnon asks, how about the G-2 discrepancy between experiment and theory prediction? Could this be related to your topics?
Yeah, well, I mean, G-2, we have, unfortunately, we have the latest G-2 experiment, or I can now see the chat. The latest G-2 experiment from Fermilab, and we have not really, we cannot say we have seen anything significant to declare victory or or anything. But people who are dealing with nuclear magnetic moment techniques to detect axions and such, they have developed a quantum mechanical NMR material that can detect axions with very, very low levels of magnetic moment. I think they go beyond the standard model. But the question is, these detectors depend on a continuous stream of axion wind going through. In order to create that level of muons so that you can have a detection, these chips have to be kind of radiation resistant. Muons are still charged particles, so you have to artificially create them and then make this quantum sensor sit in a beam of muons so you could detect it. So I think our problem is it is not robust enough electronics, quantum mechanical electronics, that it can sustain the radiation damage from the muon beam. But in principle, it can go beyond the G-2 experiment at Fermilab on paper.
Okay, so
let me see.
Then there's another question by John Ellis. MAGIS 100 may be Fermilab's flagship quantum project. What is the schedule taking COVID into account?
Right. So fortunately, the atomic expertise, atomic and laser expertise that is needed for this, it exists at Stanford and Northwestern. And those guys, although there's COVID, but these labs have just opened 2 months ago with 2 investigators at a time. So I know Jason Hogan, our colleague at Stanford, is able to work on the atomic beam and the laser system for MAGIS at Stanford. It is slowed down to 70% what it should be. Fermilab is not expected to be delayed by its engineering things in the shaft once we open up in January 2021. Our time scale is about 2 to 3 years. 2 years to complete the configurations, 3rd year to commission it, and beginning 4th year to actually interpret the data. It is delayed, of course, by COVID, so it will go to 5 years maybe. But yeah, that's life. That's life.
By the way, Jason Hogan was giving a colloquium pretty much exactly 1 year ago.
Yeah. And by the way, John Ellis is very familiar with the AION program. We have networked with MAGIS and AION. We are putting together an LOI to SNOMAS, combining the two.
Okay, so other question, according to, by Adam Jachowski, according to you, instead going to higher energies like the FCC, would it be more interesting to invest rather in the quantum entanglement application type projects?
Well, I mean, I see a lot of excitement in the young people. Like, as I said, I have surfed the wave of late 20th century and 21st century accelerators and colliders. Have been to Fermilab, have been to CERN and SLAC, and really enjoyed it. We are lucky. In those days, things took 5 to 10 to 15, maybe 20 years, but we eventually got to the building, commissioning data. Now, things are very, very long time scale of 30, 40, 50 years. So I think, on the other hand, we have not really exercised our intellect and excitement to excite the young people into thinking a bit differently to detect very, very small signals rather than creating by brute force all the energy you need to create a new particle or a new wave. So it is very exciting because it stretches your imagination, and you also have many, many applications of quantum entanglement in quantum computing, quantum devices, quantum networks. It's multidisciplinary, so job prospects are high. And if someday, after doing quantum sensing, you want to come back to a big collider, then you can come back. But I think this provides a very exciting opportunity to create our particle physics cosmology workforce who are interested in it, but who can apply their clever brains to be active and remain the engine eventually. But for the time being, there's plenty to do there. So I fully encourage younger people to get into this field, of course.
Thank you. Now there are some raised hands. Keith Baker, please unmute yourself.
Yes, hi, this is Keith Baker. I first of all wanted to say hello, Chapon, and
Hi, Keith. Hi.
Always a wonderful talk. Thank you. I also wanted to just to follow up on that comment you just made that yes, there are people starting to look for evidence for and publishing on quantum entanglement at the energy frontier and LHC collisions, and so you are correct. It's wonderful, I think, for young people to start doing this. Going back to your slide on the atom interferometers, you mentioned about having two interferometers that are separated by some distance, and therefore the distance has some delta phi in it. Are these fixed interferometers, or can they be moved? Can they be, you know, yeah. And what's the distance between them roughly? And I mean,
atomic interferometers, these are not tabletop or 10 meter like Stanford. We are talking about 100 meter, 1,000 kilometers, so LIGO scale. So eventually they would not be movable, but we are also thinking about putting interferometers in satellite, in space. And so we'll have more options there to move satellites around and create geocentric orbits and stuff. But today we are talking about, let's say we have one in the United States, let's say in the Dune, South Dakota, and we expect one to be somewhere in Europe, maybe in the UK, or somewhere in Europe, which is so distance, transatlantic distance, okay? 5 to 10,000 kilometers.
Okay.
So we're talking about terrestrial distance scales. It could be eventually space scales, and so on.
Okay. Okay, great. Thank you.
Next one is Sebastian. Please.
My question is sort of a follow-up from the last two, which is you talked about ION and MAGIS somehow working together, and I guess this is the way LIGO had two observatories, but you may actually have in mind that they're somehow complementary. And related to that, I wanted to ask whether one can profit from sort of networks of observatories in the sense that maybe for other purposes, quantum communication experiments are being done and so on, one could capitalize on the existence of those networks to add to the capability of observatories. I'm not sure if you understand the question.
Yes, of course. I mean, a network is always extremely helpful for the, if not for anything, but for redundancy. But let me just make an important distinction here. When you had LIGO, you had two setups at two different locations, and they were observing a very coherent gravitational wave propagating, and it propagates to one side, and the same wave in a coherent fashion propagates to the second side. So you can correlate the two by the propagation time of flight of the gravitational wave traveling coherently. So that's one kind of correlation, which is the coherent time of flight correlation of the two sides. What we are talking about, if we are talking about gravitational wave, which is not coherent, but fluctuational, background, random, like a thermalized CMB type cosmic gravitational wave, the kind of correlation we're talking about is actually a correlation in the fluctuation field itself at two different space-time points arising from correlation at the beginning when the wave was created. So just to give an example of optical field, light, if you take incoherent light and you take a wave front and you take two space-time points in an incoherent light at two different space-time points, they are not correlated. But if you take a coherent light, E1, E2 at two different space-time points stays correlated over the entire propagation of the laser light. So we are saying that the fluctuational field of the gravitational space-time metric would definitely have embedded in it correlations from the source. And we expect to see that correlation when we actually correlate the fluctuational properties of the wave detected at, let us say, Fermilab with the fluctuational properties of the wave detected at, let's say, UK or in EU. It's a higher level correlation than a simple propagation. So you can detect E square, e to the 4, e to the 6, all the higher order moments of the field and so on. It's a bit more detailed technical question, but that's roughly what it is. But yes, networking is extremely important. First, to benchmark, second, to have redundancy, and third, to actually get new information by correlation.
Okay, thank you. Next one is Michael Albro.
Yeah, thank you. Mike Albro here. Yeah, thanks. So you mentioned dark energy a couple of times. Now, obviously it'd be fantastic if one could measure the local value of the dark energy, but it's so very small. Do you have any ideas how one might possibly get to that level?
The dark energy is so controversial, I don't, but let us say that we take it for granted that you cannot reduce this discrepancy between from supernova studies and stuff, that you still see this gap between the actual acceleration and what it should be. And if you simply translate that at what rate universe is expanding and dark energy is being created into an energy density, you get the level I talked about, so many 10 to the minus 31 joules per meter cubed, and it translates into about 10 or 12 volts per meter. But of course, it's a constant homogeneous. If it's a cosmological constant, just a constant, the density is a constant, it is just a fixed threshold background, and you are seeing everything relative to it, so you cannot do much. It's very difficult to detect that field unless it is fluctuating in some sense. So we are looking for some kind of a AC effect of the dark energy. We hope that nothing in the world, in the universe, is constant or fixed. Everything is fluctuating at some level. Even dark energy, although you pretend it to be a constant, even a cosmological constant, may not be a constant if there are underlying mechanisms. If it is a fundamental constant, then it should show up in other physical phenomena. Like, Planck's constant, H, was initially just a fit by Planck to fit the black body radiation. He fit the formula to his equation. It was just a fitting formula, just like the cosmological constant. But pretty soon, it turned out to be the unit of energy in photoelectric effect that Einstein explained, and then Bohr used it to quantize the atomic orbits. It showed up in atomic spectroscopy. So H became a fundamental constant because it showed up beyond the black body radiation to photo emission to atomic levels. Cosmological constant is stubborn. It is not showing up anywhere, but except this measurement. So is it really a constant, or is there some underlying mechanism? If we assume there are some deep underlying mechanisms that is causing this constant to appear as an extra energy, then there must be some fluctuations in it. So we should be able to observe fluctuations of 10 volt per meter kind of thing you easily detect by squid in an undergraduate physics laboratory. So it's not a very difficult measurement.
Well, yeah, I mean, I think, yes, one does usually assume that dark energy is homogeneous and isotropic and so on, which is an assumption which may not be true. We can test it, but one would imagine that variations would be on a galactic scale rather than on a laboratory scale, right? Of course,
but we are moving everything is moving in the galactic frame. So we are constantly sampling space-time in a galactic scales. So
yep.
The hope is, that eventually it should show up somehow. I'm going beyond my depth in the subject, so I don't want to pretend I know the answer. Thanks for asking the question. But dark energy is getting to be so controversial that, yeah, I don't know.
Yeah, okay, thank you.
Right.
Okay, so there's a further question by Vaglis. A rather naive question. In a 10 meter or 100 meter atomic interferometer, each Earth gravitational field variations might be of limited significance. In a kilometer-long device, would this be still the case? Would you be affected by variations in mantle magma flux, non-seismic? And would there be a way to distinguish them?
Yes, so let me show you. Very good. And what's more, I will tell you, I had that Graph of the measurement. Yeah. Actually, what's more, if you look at the atmosphere, you have a huge almost few miles high, 10-kilometer tall atmospheric column of air, which has a Newtonian gravitational effect on the thing. So atmospheric Newtonian effects, seismic waves, both bulk and surface. Today we are only talking about surface waves between 10 and 100 meter deep. But if you go to kilometers and deeper, you have to talk about bulk waves coming from the Earth's bulk. We are measuring the bulk. If you see in this diagram, you see the big peak, the huge peak of the seismic noise. That one is the entire solid Earth moving against the water body. So it's the water and the Earth moving back and forth that creates a normal mode of the planet. So this big, huge peak is that normal mode. And we are trying to look for this tiny little sharp peaks beyond it are actually the seismic modes coming from all kinds of seismic activity locally here in Illinois, plus coming from California, stuff like that. There are also bulk modes coming from the deep underground of the Earth. Depending on the nature of the mode and its polarization, for a vertical atomic beam, we have to look into it and eliminate those effects by proper monitoring. This is why eventually, beyond 1 kilometer, we want to go to outer space. And there is a program that we have submitted to NASA eventually. They may not fund it. Anything satellite-based is just as expensive as a collider or more. But eventually we want to go to space to eliminate all these seismic and terrestrial noise sources. But then there are other noise sources, okay? So, but you are very right. All those things will be important if you're considering a, let's say, a 10-kilometer shaft, for example.
Okay, another one from Alain Magnon. Could you recall at which level you expect an oscillation of the electromagnetic alpha constant from gravitational waves?
That's so you have to translate it. I know that we are talking about gravitational waves that we can detect in the laboratory frame at the level of 10 to the minus 24 delta L over L. So let's say two masses separated by 1 meter, and we can detect a separation at 10 to the minus 23 minus 24 meter at 1 hertz gravitationally. So this we can detect. Now, how to translate that into an alpha and an electron mass thing, I have to think about it. People have calculated it, and that was at the basis of this graph I showed you. I have to, this one, I cannot give you a quick number quickly. I cannot give a number. Very
not precisely sure what the question meant. I mean, he was asking for the electromagnetic fine structure constant as being influenced, or the measurement being influenced by gravitational waves.
Right. He's talking about his. Oh, I see. I see. I understand the question. It is not the dark matter interacting with the atomic levels, but gravitational wave interacting with the dark matter.
With the electromagnetic interactions, I think.
Yeah.
Maybe, Alain, you can pose your question maybe differently.
Well, this question was, in fact, as you know, there was many progress the latest year, in particular by the Yale University Vernon Hughes, to make extremely precise measurements of alpha. And I'm not expert in these new waves, but people ask me at which level could this oscillation of alpha be seen. That's all. That's maybe a naive question. Okay.
No, it's not naive at all. That is exactly at the heart of this figure I've shown you. Is this oscillation of the atomic levels is coming from multiple sources. It's coming from direct coupling of alpha to the dark sector in whatever way. Direct, so which will also mean the electron mass would change. That means the atomic levels would change through alpha and the electron mass. There may also be coupling because we are looking at coupling of the entire sector of electromagnetic strong, weak, and gravitational wave from the Big Bang. There may be some low level of coupling there. But all I can tell you is that our atomic beam is sensitive to 10 to the minus 24 delta L over L at 1 Hertz. And I must be able to go back and calculate what that implies for the coupling of that sort of a thing to this thing. The alpha fluctuation, people have calculated them. I have to go back to the reference and tell you. I cannot tell you correctly.
Okay, thanks a lot. My previous question concerning G-2 was in fact related to, there is, as you know, this 3.5 sigma discrepancy between standard model and there will be a future measurement. But I'm involved also in future experiments at CERN, like the muon E, which wants to measure more precisely the hadronic component. So I think this discrepancy of G-2 is extremely important.
Right.
Thank you.
Okay, so no more questions. I think we can close the session.
Let me.
I want to make this the play.
Right.
Yes.
So you know the Bose-Einstein, they have wrote 3 papers together. Einstein played violin. This is not him playing the violin, but just to tell you, this is how it sounds. I leave it up to you what piece of music that is being played on the violin. It's not Einstein playing it, but his favorite music. But now this is Bose playing an Indian instrument, and this is his original music playing called Esraj. Very rare piece.
Are we supposed to hear something? I don't hear anything.
You don't hear it?
No.
Oh, okay. I don't know. So something is okay. Maybe you didn't. Okay, you probably did not connect it. Do you have it? People's laptops must be connected to the sound.
No, we don't hear it.
No, we don't hear it.
Okay, forget it. Forget it. Okay. Thank you, Wolfgang.
Yes, Swapan, thanks a lot for the wonderful talk. It was a lot of audience, like 220 or so.
Right.
Yeah, okay. Thanks a lot.
Thank you.
And
Bye-bye.
I will post the recording. It takes a few days. It will be available on the website.
Thank you.
Okay.
Would you post the recording of Bose playing the instrument also, Wolfgang?
Yeah, no, actually, Swapan, if you send me the sound files separately, Dropbox or something, then I can also put them in the site.
Okay. Thank you.
Okay.
This photograph you see, Wolfgang.
That's Himalaya, obviously.
No, this is where I grew up.
Mm-hmm.
It's the town of Darjeeling, where the tea comes from. It's the Himalayas, 28,000 feet altitude. All right. Thank you.
See you.
Bye-bye.
Bye-bye.
Bye.
Thank you. Bye-bye.
Bye-bye.